So, hello everybody. I'm coming to you from a dark hotel room in Connecticut. It's 4 a.m. in the morning, so welcome. And we're going to talk about how to get trusted column store perform well. While it's a great feature, one of these many features inside SQL Server that needs a little bit help from you and me make it actually go fast. That's what we're going to talk about today. My name is Thomas Grohser. I'm with SQL Server for 25, 26 years now. I started with version 4.2 and basically use it to scale their solutions. Here, my email address will also be on the last slide. So if you have then questions that you can't ask here or doesn't get answered here, you can write me an email. So enough about me. This is about the agenda. So basically 3 steps. I'm going to talk how column store works. This is basically so that we all have the same understanding where we are. And then the more important part is what to do and what not to do when using trusted column store. And then we will have questions. I will break for questions in between sections. So please be patient if I answer them not immediately. These are the sponsors. Please visit them in the expo hall when you have a little bit of time. So before we start with column store, let's revisit how the good old row store that's around for 25, 30 years stores data. Basically, every row has a row header, which is a couple of bytes that tells SQL Server what type of row that it, what's in it, how big it is. And then column by column gets added into basically an array of bytes and the next row looks very similar. The fields might have different sizes because they are variable length texts, but that's basically it. So row by row is stored in some way. And then these rows are placed on a page, and they are placed on the page in a very random order. And then there is a slot array in the bottom of the page that actually puts them in order, but physically they might not be. Thing is, Microsoft scrambles them around and stuffs them in so that they fit best and they don't have to rearrange everything every time. And then they use that at the end. And then there's page by page. So this is how it was for a very long time. No difference anywhere. And then next page and next page. And this continues thousands and thousands and millions of pages, larger databases. Okay, so with that, what's different in column store? So in column store, same table would be stored, column A, and then it would be row 1, 2, 3, 4, 5, all the way down to about 1 million. And then column B would be stored separately, again, for each and every row, the value, and then column C and so on. And these up to 1 million rows of each column are called a row group. Yeah? So B row group 1, and then another row group of the same, very much the same, would be below that. That gives it the advantage that only load the columns it actually needs. So if you only select column A and C, it would not pull in the data from column B, work on it. And if you have very wide fact tables, that can make a big difference just by that. So the first thing we learn is don't do select star from column store tables. Yeah? Only pick the columns you actually need. because while in row store it made only a small difference, in column store it makes a big difference if you read all the columns or not. In row store, SQL had to pull in the whole page, the whole row anyway, so if you select the data or not didn't make much of a difference. Column store, you have like 100 columns and you select only one, you are 100 times faster than if you select all 100. Very simple. Yeah? So that's the first very valuable lesson I can give you. Yes. So look at this picture at the side. How SQL internally actually stores that is, it would take column A, first row group, and then compresses it as much as it can. And it's amazing how much Microsoft managed to compress this thing. If you, for example, have an ever increasing integer there, the 1 million values probably take up 2 or 3 bytes. If you have a repeating date, same thing, couple of bytes. Yeah, they have a handful of different compression techniques, and they look at each and every column of what data is in there, and they use different compression algorithms for each data type and each based on the type of data it's data find in the columns. So column A, what they have in the background is an actual regular table that has a row identifier that says this is column A, row group 1, and then it gets compressed there as the thing is. And then the same, this is stored in a var binary max. And then the same happens for row group 2 for column A. Then we repeat it for each one of these columns. And this is how they can only select certain column. So if you do a select column B, it will only pull the purple values out of this other table and then as needed. How under the table is. Under the covers, they store the data. That will be very important information coming soon. If you want to learn more about little bits and bytes, how it's done under the cover, 2 sources. One very excellent talk from Bob Ward a couple of years ago at the PASS Summit. And I will share these slides at the end, and the links are working. And the other one is Nico. He basically has dedicated his life to column store and has written several hundred blog posts about it. So that's where you can find these. Let's talk a little bit about the history of column store. Column store was one of these features that Microsoft released before it was actually ready. So SQL 2012, you could have a regular table and put a column store index on top of it. That was great, but in the end, you had the data twice. And it was read-only. So once you created it, you couldn't insert any new rows. So not many people used it. There were techniques how you could overcome this, but yeah, people were not happy with it. In 2014, they added the clustered column store. That's the one we're talking about today, where like with a clustered index, clustered column store becomes the table. It's the only place where the data actually exists. And they made insert, update, and deletes possible. I put emphasis on the word possible because as we will go on, I will show you why it might not be a good idea to update or delete your data. 2016, finally made, if you have a column store as a secondary index, you can finally now edit that one too. You can filter them, and they added a possibility if you have a clustered column store, put a regular index on top of it in case you need to find something or in case you need to enforce like a unique constraint. While this sounds like a great idea, I always shied away from it. And the main reason is that the regular index on top of it doesn't benefit from the compression. So usually that index is much, much, much larger than the actual column store. And as we will talk during this thing, the optimizations I did were much better for performance overall. Yeah. If you need visual rows from a column store, don't put it in a column store. Keep it in a regular row store. Column store is for scanning across lots of data and not for finding one piece of information quickly. 2017, they finally added computed columns to it. And in 2019, they made the builds and the rebuilds online, which is very important because if you have very large tables, that takes a while and you don't want to go offline while rebuilding. And you have to rebuild them in case you do insert updates and deletes after the initial load. So that's the history. Okay, so the goal for this session is I want to show you how to build a column store, a fact table in a data warehouse most likely, that returns query results quickly even when you have billions or trillions of rows that have to be queried. That is a challenge I had to solve, and it is doable. So we will go through how this works. So the solution. That was the goal. So as I said in the intro, column store needs your help. If you just throw random data at it and don't make any kind of changes to your way you're treating a table, if you treat it as a regular table, you will not have a good experience. If you treat it with certain rules in mind and be careful, then it will be a very good experience. So first, you need a nice database to put it in. And so we can create data in row groups. As I said before, row groups are stored in bar binary max. And that is a blob data type. And blob data types have one problem, that can't rearrange them once they are stored. Also, to make column store happy, it needs to be partitioned. Yeah. While with a regular table, if you partition it, you will normally not see any performance differences except in very rare cases. In column store, it's a gigantic difference. And the next one that we will go through in detail is only use data types that column store likes. I will show you which ones they are. While you can use any data type, column store will handle it. Some of them it handles much better than others. And where we go. So first, the database. As I said, it's bar binary max. That means you cannot shrink data files that contain a column store. If you try that, what happens is to move one page to another location in a data file, the server has to do a full table scan on the table that owns that page. If you have a couple of gigabytes, that might still be doable, but once you get into the terabytes, that will take a very long time. That's not some optimized quick scan across it. This is meaning read all the data. For whatever reason, that's how SQL works. So be prepared. However you create your data files, that's the way they're going to stay. You can still grow them, but if you delete some data, it's almost impossible to shrink them. So normally you have to completely rebuild the clustered column store to make that happen. Just a warning. Yeah. So that just means please plan ahead when it comes to creating the database. Just a fair warning. I usually put the column store in its own file group and that's the only thing that lives in that file group. And the only reason for that is so I have it separated so I can still manage the rest of the database. If the rest of the database is basically non-existing because it's just a couple of megabytes of lookup tables, then you can put it all in one file group. But if the clustered column store is a smaller part of the database, I like to put it in its own file group. And I like to give it between 12 and 24 data files so that they stay small and are still manageable, because remember, I can't shrink them, so I like to have smaller files to begin with. You can put them on the same volume. It's just to have more files in the beginning, because if you ever have to split it up, again, it's not happening. Yeah? It's can't move the data from one file to another once it's created. Inserting data. So, create a clustered column store. It sits there, it's empty. So how do we most efficiently insert data? There's two new friends you will make right now. One is this magic number, 1,048,576. This is how many rows you should insert every time you insert in a clustered column store. You can insert less, you can insert more, but in a few seconds you will learn why not to do either one. How does this number relate to anything more computer thing is? If you take the square root from it, it's 1024. So 1024 times 1024, and that's the exact number of rows that can fit into a row group. The idea is you want to put exactly that number into a row group. Why I'm warning that? If you insert less, this is the perfect. If you manage to insert that many rows at a time, you will have the most efficient compression and the most efficient way of getting data out. If you insert less than 2,400 rows, they are not actually stored in a clustered column store. They are stored in a regular row store that they call a delta row group. So it says this is so few rows, if it's less than 100,000, roughly, we're not putting that in a column store because that's not worth putting it there. Yeah? So they put it in a regular table. And then every time you query, they have to read the regular table plus the column store and union the result. And that makes it insanely slow. So if you insert more than 102,400 rows, but less than the 1,048,576, they are stored in a row group, but not all possible slots are used. So you're basically letting stuff empty. And we will learn later why smaller row groups are inefficient. If you insert more than the magic number, SQL creates one row group with the exact number of rows that the magic number defines, and then proceeds with the rest as before. So if you insert 1,048,577 rows, it will create one perfect row group and then insert one row into the second delta row group in a second table. Yeah. So try to insert that number. You can insert exactly twice as much or 3 times, 4 times as much. That's fine. Then SQL breaks it up nicely. But that usually also becomes then a very large number of rows that you don't want to do in a single insert. And things. So to learn how to insert that many rows at one time, it can only be a bulk insert. It cannot be an individual insert statement, because an individual insert statement, even if you specify multiple rows, there's a limit of 1,000, which is not even close to the number we need. So you either can transfer it from an existing table into column store, or if you are still outside of SQL Server, you can do a direct bulk insert into the table, but make sure that the bulk contains exactly that number of rows. Compression is done within a row group. 2 half-full row groups compress less than 1 full one. Why? Because they will have separate dictionaries, they will have several starting values, so that's why the thing is. And 2 half-full row groups will also have twice the metadata. Yeah? So again, try to fill it up as much as possible. If you, for whatever reason, cannot insert it cleanly, you have to rebuild the clustered column store index after you insert to get to the same performance as if you would have inserted directly. Well, this might be a good idea while the table is still small. Once it reaches a certain size and the index rebuild takes a day or two, that might not be the best plan. So if you can manage to insert that many rows at a time, it's much better. This is the architecture how we inserted data in a very efficient way. So we had some process outside of SQL Server that was creating the data, and we used the bulk API, put it into in-memory OLTP tables, because we could not guarantee that that process would have the 1 million rows at a time. So we collected it in an in-memory OLTP table and then had an agent job that waited for the 1,048,576 rows to be in that in-memory OLTP table. And if they were there, it grabbed them out and put them into the column store. This agent job was running every couple of seconds, checking the in-memory table. That is a very quick one. Hey, we have more than that many rows. Take the top and put it into column store. And that also, this part was inside SQL Server, and this part was in the application server. The nice thing is that over time, we could add more and more application server, just randomly pushing data into the in-memory table. So that turned out to be very, very good. With this way, we processed several billion rows per day and had very, very efficient column store after inserting this way. Again, you don't have to, but if you don't have to, don't complain that column store is slow. Deleting data. So, good news and bad news. Good news is, yes, you can delete data. Bad news is, you don't actually delete data. Data is not deleted in a column store. If you delete it, what Microsoft does in the background is, it creates another table and inserts the rows you want to delete. And then every time you query this thing, it subtracts rows from your result set. So we learned before that if you don't insert well, they create a second table where they put the small number of rows in that they have to then union. If you delete, they create a second background table that now contains the rows thing is. And since there is no primary key in a clustered column store, they have to store the whole row. And then they have to compare each and every column that you selected. If it's a match, yeah, the moment you delete a row, you basically, it's like when you're in a car and you switch from the 5th gear into 1st gear on the highway. That's what's happening. So if you delete data, after you delete data, you have to rebuild the clustered column store index. There's no other way of getting it clean. Yeah, it's not doing something in the background and eventually gonna clean up or so. It's just not. You have to clean up by rebuild the column store index. Performance is horrible the moment you delete. So that's the bad news. Moving on to updating data. Yeah, it's worse than deleting data. Why? Because an update is a delete followed by an insert. So Step one, create an extra row in the second table to mark it as deleted, and then just insert the one row into the first other table to make sure we have the new values. So now every time you query column store, Microsoft in the background has to do a three-way join between these two tables to give you the correct data. Just don't do it. Yeah, so data plus delete, copy plus integer every time query. Yeah. If you have to update data in a column store, rebuild the whole thing after you've done it. Otherwise, you will not. It becomes very, very slow if you're updating data. Good. Before we go to select, I will check one more time if there were any questions so far. No, nothing great. So I'll continue. So, selecting data out of a column store. This is where it gets really funny. First of all, the only way to access a column store index, and this is funny why Microsoft calls it an index, is a full table scan. If you select a column from a column store, the only way SQL Server can process that column is by reading each and every row of that column. Yeah? Why they call it an index, I don't know. I've never found the person who named it. So, thing is, be a little bit more precise. It's a full table scan with partition elimination if the table is partitioned. And this is why I said it's so important to partition the column store when you use it. Because the partition is basically a little bit of indexing you can do. For example, if the simplest partition you could do is like by year. Yeah. So every year you create a new partition. So if you now filter on a date that contains a year, SQL Server only has to read the one partition that contains that year. Let's say you have 30 years of data, that just made your query 30 times faster because instead of reading 30 partitions, it only has to read one partition. I think you get the idea with column store, how simple changes can make performance go faster. So we had the first one that if you have 100 columns and you select only one column, it's much, much faster. Second one is if you have partitions and you can filter on the partition, you also reduce by a lot. Yeah. My suggestion and my advice is to partition by common search argument that narrows down the number of partitions a lot. Yeah. That's easier said than done. And usually dates are a good start, especially in data warehouses, because normally there's always a date range involved, but you might become clever and do even more. So, for example, it's not exactly what we did, but thing is, yeah. First of all, there's a partition limit. You can only have 12,000 per table, but if you read the internet, everybody that used more than 3,000 started complaining that SQL doesn't behave very well. So what you should think about is that your end state should not have more than 3,000 partitions. And that's a lot. And basically, if you can filter based on partitions and you can bring your query down to one partition at a time, that makes scanning the table 3,000 times faster already if you actually use all 3,000 of them. So that's a good start. So, as I said, date is usually easy, but you might want to create a surrogate key combining several keys, make it more efficient. So, for example, what we did is we took year, month, and product group. Yeah? So we stitched it together into one number. And the query, when we used the store procedure to query it, where we passed in all three separate parameters, store procedure made that funny string again that we used to fill the table, but it allowed us to partition because we had about 50 product groups. we designed the number to be able to have like 10,000, which we would never reach. And the dates were clear to begin with. So that let us narrow it down, not just by year and month, which were most of the time we reported on whole months or whole years. So that was very helpful. And then the second one, the product group, it's usually most of our reports were limited to one product group at a time. Yeah. And in your company and in your database, that might be something very different. Yeah. It might be like the first digit of a zip code, or I don't know. It's not a product group. It's like an device type or something else. Yeah. Depends what data you're storing in. But think about it. If you can do that, the idea is to slice the data into about 2,000 to 3,000 pieces over time. And if you can do that, you can narrow down that table scan massively. Good. So data types. And this is where it gets really interesting. Yeah. While Custom Column Store can handle almost every data type, it prefers certain data types over others because it can use them much more efficiently. Meet your second new best friend. So we remember the 1,048,576. This number is much easier to remember. It's 8 bytes or 64 bits. Every data type that fits into 8 or less bytes or 64 bits or less can be extremely optimized in Column Store. Column Store just loves them and processes them super efficiently. So these are the data types that work. Big int, float int, binary 1 to 8, small int, character 1 to 8, national character 1 to 4, which is very short but still doable. Tiny int, datetime, datetime 2, time, money, small money, and regular date. So in simplified words is, don't store large strings in Column Store if you can avoid it. You can still store it, but don't query it. Sounds funny, but as we learned at the beginning, if you store something in Column Store in a column and you never select a column, SQL doesn't touch it. It doesn't look at it. So if you need to store text for whatever reasons, might be for regulatory reasons or something like this, but in most of your queries you're not using it, it's still fine. But the columns you actually want to query, they should be 8 bytes or less. And the reason for that is SQL Server uses a new technology that is in CPUs for quite a while now, so they can actually use it. It's called SIMD. So what they're doing is single instruction, multiple data. So what they can do is they basically load a bunch of data into a CPU register and say, hey, these 4, this is not 256 bits. This is actually 4 times 64 bits. And instead of working on one of them, work on all 4 of them the same operation. And that basically makes the CPU do 4 times the work in one thing. And presentation of Bob Ward I mentioned before explains exactly what they're doing. Yeah. So the next thing that Column Store can do is, if you have simple filter conditions, it can push down the filter into the storage engine. That means that the query engine that processes the query doesn't even get the data. So it's filtering out the data before it gets created, before it gets selected. Yeah. In a row store, you would have to load the whole data page from disk, or then scan the data, return column X, and then look if column Y is in 7 or between 7 and 25, and if it's there, it will use column X. In column store, if Y uses more than 8 bytes, then load column X and Y from disk to memory, ignore all the other columns, and do the processing. If column store, column Y uses less than 8 bytes, storage engine just returns the X values for which Y is between 7 and 25. It doesn't even return the rows that are not there. So that's done. And that gives you a lot better performance. Just imagine you're looking for like one value out of a couple of thousands, and scan through, and only the rows that match come back instead of all of them, and then have to be processed. So same works for aggregates. They can push down aggregates into the storage engine. So that allows, if you need a sum and average from a value, the storage engine that contains the data will already return the result, not return all the individual rows. So instead of a row store, it loads all the data pages. It has to calculate the aggregate. In column store, if it's more than 8 bytes, it loads the column from disk, just the one, and then calculates the aggregate. If it's less than 8 or equal to 8 bytes, storage engine returns the aggregate and is done. So you see, that's another big potential for faster query results. Query must then process a few values for the overall result, because you're getting an aggregate per row group. Still much more efficient to get, basically, like, sum up 1 million rows before summing up lots of these individuals. Good. The next one is row group elimination, and this is, after partitioning, second best that column store does. If you have columns that use up to 8 bytes, column store keeps a min-max value for each row group stored in the underlying table. Very simple. So if you store numbers and you insert numbers, and these are, for example, ever increasing numbers, in the first row group, it's say minimum is 1, maximum is 1,048,576. And the next one, it says minimum is 1,548,577, and max is whatever that number times 2 is. So if you look for something, it scans through and gets ready to pull out this data, and you have a filter on a column that is less than 8 bytes, it will look at, hey, is this range, is this number that you're looking for in that range that we have for this row group? Nope. Let's not even process it, because we know it's not there. So, works thing is. So, for example, if row group 1 contains custom IDs 1, 3, 4, 5, 6, and row group 2 contains 8, 9, 11, and 15, and the minimum and maximum values would be 1 and 6, and 8 and 15. So if you were query for number 9, the first row group would be ignored, because 9 is larger than 6, so we don't have to look at it. But it's going to be, might be values in the second row group, so 5 and between 8 and 15. So SQL Server will only look in the second row group for data. The hint I want to give you here is, if you really insert lots of data, you might want to pre-sort that data. We're already sorting it kind of by partition. So we insert data into one partition at a time. But then you can pick another column to be like your primary row group eliminator. And so we've done before the date and the product group, and now you want to make sort it by custom ID. So if you want to filter by date, product group, and customer, you can use the partition and row group elimination to get to a very small amount of rows that actually need to be processed. So if you can keep more than a couple of million rows in your buffer table, pre-sort that table before inserting it into things. And the sorting is by the first column that you want to filter a lot on that is not inside the partition. You have to insert 1,048,576 rows per partition, but within the partition, then you should sort it by custom ID if you do multiple of them. Just, again, helping as much as you can. Yeah? If you can't do one of them because that's not how your data gets created, it's not tragic, but if you can, do it because it makes it much faster. Next one, batch mode. So, if all columns in a query are columns that use 8 bytes or less, SQL switches to batch mode, which processes about 900 rows in one go instead of row by row. And this again has to do with these new CPU instructions that let SQL Server work on 4 8-byte values at a time. If you take that plus the overhead, that's exactly how much fits into 64 kilobytes of data. So basically they fetch 64 kilobytes of data from the column store and then process 8 columns at a time with 4 columns at a time. And that gives them 900 rows to fit in one go. What's the difference in simple word? It eliminates the back and forth between the operators in a query. When you have ever looked at a query plan, you see these nice little icons and the data basically moves from one to one. In regular mode, in row mode, it basically takes one row and moves it through that query plan. If you have batch mode, instead of doing one row at a time, it does roughly 900 rows at a time. So what's the difference? A real-time, real-world example, you have 3 clerks working in an office. The first one fills out a sheet of paper, gets up from his desk, walks over to the desk of the second guy, drops the sheet of paper, and then walks back to his desk and starts working on the second sheet of paper. Second guy now has 1 sheet of paper, works on it for a while, and then gets up and moves it to the third desk, and so on. Yeah, this is super inefficient. If the first guy would work on 900 sheets of paper, once done, gives the 900 sheets to the second guy, then this one can work on it, and so on. Well, that's the big difference. Again, batch mode, just much faster. If everything's 8 bytes, it works perfectly and kicks in automatically. You don't have to do anything about it. Again, the 900 rows, modern CPUs have SIMDs. That's the explanation directly from Bob Ward's presentation. How they work is process 1 row with 4 different columns at a time. It's just pure magic. So, what about data types that are larger than 8 bytes? Don't use them. But if you have to, you will just not get any of these optimizations. It's very simple for them. Yeah. If they just sit in the column store and you don't query them, you're fine. If you query them, expect the result to come back much slower. What I've done in my cases, I've created a star snowflake schema and referenced this data out. Yeah? So For example, one thing we had to store in our table was like computer names, and there were more than 8 bytes. So what we did is we knew that's a very finite number of names we're going to have, because you normally just have a couple of thousands of them in your organization that created the data. So we had a reference table that had all the computer names in it and a short int ID that we then put into the column store. Yeah? We needed to query. We first did a query of figuring out this is the computer name, that's its number, and then use that number in the select statement. So we didn't even do a join. So we freed SQL from the join because we knew we were always going to be filtering on one computer at a time. If we would need 10 or 15 at a time, we would have used the join, but to make it as simple as possible and to get all these push downs, used a lookup query before that. Archiving data. Column store comes with 2 levels of compression, regular and archive compression. Regular compression is just faster to decompress than archive compression, but also needs more space. And with more space, that is a very, even in regular compression, column store is good. But in archive compression, it's even better because it takes more time to figure out how to do it most efficiently. Time to query it. Yeah. So here is one bad news again. You normally want to have some kind of archive, and the best idea of having an archive is to have it on a different box. That is older, smaller, and just but slower. Don't need the data that often. The problem is when you transport the data between 2 systems, you're not transporting them compressed. So if you have the data in a column store on system A and you send it over to system B, it completely uncompresses and then recompresses it. That means the network between them needs to be very, very big because it's many times more data than you have on disk. So be aware. Looks like, hey, my column store, this partition only has like, I don't know, 100 gigs in size. So let's move that to the archive. But then you figure out, hey, we have like a 1 to 30 compression. So the 100 gigs are suddenly 3 terabytes. And that might be much more work than you anticipated. Fortunately, technically, Microsoft could move the compressed data, but as of now, they're not doing it. So backups. So that's more for the DBAs, less for the developers. But column store still compresses when you do turn on backup compression. And it still compresses a lot. So yeah, if you take backups, it still makes sense to compress the already compressed column stores. It's, as I said, they are stored in regular tables, so there's plenty of overhead in the page headers for Microsoft to compress. And backup compression uses a couple of assumptions because they know they are compressing pages, so they can do a very good job there. Where are the limits? A very good question. I don't know yet. So far, I haven't found one. The largest column store I worked with a year ago had about 3 trillion rows. And that was inserted in 2 years. So by now, it should have probably 4.5 trillion rows. It works just fine. It has no issues. The issue is it's 15 terabytes on disk, the column store size on disk. It's 15 terabytes. So it's large, but it's not like huge. Yeah. So I've seen bigger databases, but 15 terabytes. Problem is, or or the fun part is, a row has 168 bytes of data, and the way column store compresses it is 1 to 32. So each row takes up roughly 5.5 bytes store. So that means that the row store, if we would convert that into a regular column store, to a regular clustered index, it would take 0.5 petabyte of storage. So while I said querying it is awesome, moving it to the archive server, not so much. The way we literally archive is we take a backup of the primary database, move it to the archive server, restore it, and then do the recompression into archive mode there. We try to move the individual rows at the rate we are inserting. It makes no sense. We have to get it all out. Where are the limits, part 2. Our goal is to have a query time of 10 minutes or less for most common cases we optimize for. And to sum up what we did in this whole thing is, so we do usually count stars, sums, average, mins, max, all kinds of things to our data that we are interested in. And that we get through aggregate pushdown pretty good optimized. We do a where clause on usually the date and column A. Column A in our case is the product group. Yep. And this we get, if we do this, we get the partition elimination. Then we filter most of the time on column B, and column B is the one we pre-ordered the data before inserting it. So we get row group elimination for B. And that means right now we already reduced the number of data that we're looking at a fraction of the whole thing. So from the 15 terabytes, we are now looking at probably 30, 40 gigabytes. We have built on one more column, which will give us filter pushdown. And then we usually group by a couple of columns, which gives us aggregate pushdown again, that the group by is also handled in the aggregate pushdown. So with all that in mind, we run this result in batch mode. And every time we had to make a change to any data, we rebuilt the partition where we had to delete or update data to just make it nice again. And okay, good. Thank you very much. There's my email address, tg@mylastname.com. I will now switch back to the application. Probably should stop sharing my screen. Are there any questions?
Yes, we have some questions in the chat.
Here we go. So info about deleted row delta store or in a structure deleted bitmap. No, it's literally the same row is in there so they can identify it. But the problem is there is no practical event. I was a little bit late. Yes, I will share the slides. Hopefully someone from the conference will tell me where. But yes, you can have the slides. If not, if you just Google for the title, they are all much out there. So it's fine. And I think there's even a recording of that session somewhere on YouTube. How do you handle fresh data that you haven't yet inserted into column stores? Yes. So in this case, we were a little bit lucky because we only need yesterday's data. We don't need today's data. If we would need today's data, I would do a union between, I would run the same query against my buffer table and the other table and union the results. It's still faster than doing bad small inserts. Okay. Typing, that's
So does it mean that you extensively use in-memory tables then?
We use a couple of gigabytes in memory table. Yes. Extensively, no. I've used larger ones in memory solutions. Yeah. We basically, what we found is we let it accumulate about 50 million rows. And again, there are 168 bytes wide. So it's not like gigantic. It's a couple of gigabytes. And then we select 48,576 at a time for column B, for the partition plus column B, and we order it by column C, then insert it. Yeah. And that usually gives us a good turnaround. Yeah. So we keep about 50 million rows in the memory table, and then pull the ones out that are ready to go. Yeah. Again, we're lucky that we don't need the data immediately. This is more like a long-term trend analysis than who just bought the product a minute ago. That's the line. Is a good strategy to split longer than 8 byte if you have to filter on them. If you need to pull them in, yes, you could split them, but be aware that filtering on them might be really hard if you split them into multiple columns. So the question was, it doesn't make sense to take like a 16-byte string and store it at two 8-byte strings. Yes, it could be. You would have to test that. Normally, we got more successful with having a lookup table if it's repeating strings. If it's repeating strings like city names or street names, yeah, this is a very finite number. If it's some random text that is different for everyone, again, you can store it in one big go, but if you select it, it ruins your query. Yeah, that's what it. Yeah, no, it's if you concatenate it, it's not searchable. Yeah. How does column store know which data from one column is connected to the other one? So it's always the exact same number of columns. Sorry. So it's always the exact same number of rows. So row number 7 is always stored at the 7th position in each column. Yeah. So that's how they know which ones belong to each other. Yeah. When you sort it, you sort them all. You're not sorting them column by column. You sort the whole row, but then store them by column. Does this make sense? Yep. So there's always so even if there's like a null value, they have a little marker in there that says there is no value here. Yeah. So that's how they know.
And how can you tell that the aggregate pushdown, for example, is in action? Does it somehow tell in the execution plan?
Can usually see that in the query plan that it says somewhere push down. So the query plan, you might not see it in the GUI, but if you use the XML query plan, it's there for sure. Everything is there. I hope by now, I haven't checked in a while, that Microsoft actually got Management Studio to show it. But it's definitely in the XML query plan that you can pull out. How about big varchars which are filtered by integers? So yes, so if you just select a big column that is more than 8 bytes, it's not ruining it as much as if you filter on it. Yeah, but it's still ruining it because it can't use that parallel work on multiple rows at a time thingy. Yeah. You will still get a decent result if you're just reading a big column, but it's not as good as if it's not there at all. Again, it's not a never do this. It's just if you do it, expect it to come back slower. Yeah. So if you can avoid it, avoid it. Sometimes text data is just there for convenience, and you might be able to shorten it or yeah. Someone just made a remark that when they had like NVARCHAR 4000 and they tried to group it, it ruined their happiness. Yes. It's just if it's there, it puts it's a hurdle. Yeah. And again, sometimes you can't avoid it, then there's no way around it. But often it is, because as I said, lots of text strings are just repeating ones. Then I would put them into a dimension. If they are completely random or so, yeah, there's no other way. Does each partition have its own delta row group? Good question. I don't know. It could go either way. They might partition the delta row group the same way that the main table is partitioned. That's my best guess. But don't call me out on it if it's wrong. It might be. So it wouldn't make sense for them to create, like if you have 100 partitions, to create 100 tables. So it would only make sense to either have one delta row group for everything, or have it partitioned the same way than the main table is partitioned, that the column store is partitioned. That's the only thing that would make sense. So yeah, so we are over time already. So, but big strings is still better for reading. Yes. So yes, it's still better than storing a big string is still better. Yes, you get better compression and it's still better. Yes, it's where you want to be. You have a regular car, then you have a sports car, and then there's Formula One racing cars. Well, what I tried to convey today is how to get to the Formula One racing car. If you're happy with a sports car, stick with that. Yes, it's better than having an old beat up station wagon. Yes, yeah, you're correct about that. Yeah, and again, it's always, if unsure, test it. Yeah, it's okay. Everybody, thank you very much. I have to free the stage for the next speaker. I hope you have a great virtual conference, and hope to see you all in person maybe soon, in a year or so. You, and I will find out how to share my slides. That will be my mission for today. Thank you very much. And
Thomas,
yeah.
I will contact you.
Yeah.
Directly messaging the Salvatorland.
Yeah. Send me an email and I'll send you the slides. Yeah.
Okay.
Perfect. Good. Bye, everybody. I go back to sleep.
Have a good sleep then. Bye. Thank you.
Yeah. Bye.